And then we're going to go, okay, I'm going to subtract out the triangle, and I'd be left with that area. So it's sector minus triangle gives us that segment. So we're going to go sector minus our triangle. All right, sector area. Sector area is going to be your degree of your arc divided by 360 times pi r squared. So our sector area, we just need to come up with this x degree length. So I need that right there. Can someone give me what that x value is right there? Oh, I erased it. I meant, what is that? That x right there. 90. It is 90 degrees because this is a central angle. So we are going to have 90 degrees up here. So our sector area, our entire sector area would be 90 divided by 360 times pi r squared. Well, pi, our radius is 10, so it's pi times 10 squared. And then we're going to subtract away the area of our triangle, where our triangle is half of base times height. Half of base is 10 times 10. And we are going to end up with 25 pi minus 50. So the correct answer was C, 25 pi minus 50. That is the correct answer for our area. Yes?
I don't get why do you have to subtract it from the triangle? Why can't it just be 25 pi?
25 pi is this area here. That right there is 25 pi. I don't want that. I want to subtract out this triangle to be left with that little section there. So once again, 25 pi is all of that. I don't want that. I want the little segment, so I want that. All right, and then we're supposed to find the arc length. Well, arc length is still going to use that 90 divided by 360. But this time, instead of using the area formula, since I'm looking for length, I'm going to use the circumference, which is 2 pi r. So that'd be 2 pi times 10. And this just ends up being 5 pi, correct? Is it just 5 pi for that one? Okay. So that one should just equal 5 pi. Well, yeah, it'd be 1/4 of 20, which is 5 pi. Yeah, we're good. 5 pi. Any questions on any one of those two? Test is on Tuesday. I guarantee we have problems like this. These are probably the easier questions. These are the ones you should fire through. The ones that are just straightforward segment. So make sure you know how to do those. All right, questions from the homework. That one. Julianne. 11. Do you have a specific question or just like setting it up or?
I just didn't know your thought process.
Okay, cool. All right, so we have people talking that shouldn't be. We are going to have L, M, N are midpoints of triangle ABC. So if I draw a triangle ABC. And I have midpoints that are L, M, N. So we have L, M, N. And when I connect those, we're going to have lots of congruent segments. And that will look like that. Well, we can actually prove that all 4 of these triangles are the exact same size. We have proved it. You can almost see it from these being congruent and having similar stuff. But all 4 of these triangles are the exact same size. So when I'm comparing the areas of our big triangle to our small one, the area ratio is going to be 1/4. Because I'm comparing like one small one and the big one is 4 of them added up. So our area ratio is 1/4. If my area ratio is 1/4, what is my scale factor going to be then? 1/2. Our scale factor would be 1/2. Does that ratio kind of make sense? Or it could have been 4/1, depending on how you set it up. Okay? Is that a little clearer why I did what I did? Okay, good. Hamza.
Yeah, so
So for this one, how do we know though that all 4 triangles are?
We have proved it like twice before.
Okay.
I'm not going to prove it again.
Okay.
It has to do with, we could prove that all these angles and all these, and we actually have a theorem that says that they'd be all 4 the same. Other questions? Brendan? 14. 14. First of all, we have to figure out which 2 triangles are similar. And we're going to use a big fact that some of us forgot, and I had to walk around and help you on, which is 100% fine because we haven't talked about this for a while. But to prove that 2 triangles are similar, you have to show that 2 angles are congruent. Well, the first angle we can prove is congruent is A is congruent to A. So I'm looking at this triangle here, and I'm trying to compare it to this triangle here. Those are the 2 I'm trying to prove are similar. Well, that's one angle. The other angle I can prove are congruent is this angle here and this angle here. And I'm drawing them just like that. Maybe I'll do one in green, actually. Both of these angles are inscribed angles. They're inscribed angles subtending the exact same arc. And we have a theorem that says, well, if you have 2 angles that are subtending the same arc, they're going to have the same measure. Another way you can look at it is, let's say that B to D is 50. An inscribed angle is half that measure, so C would be 25. And E would also be 25. So E and C must be the exact same length. So then we can say that our triangle ABCD is going to be congruent to ABEA. So that's the statement I have down here. ACB is similar to AEB. Then it says find the area ratios, and then we're supposed to find a specific length. Well, our length ratio would be AD matches up with AB. In other words, AD is the same ratio as AB, so it's just 10 over 9 because those are our corresponding sides. So our scale factor, our length ratio is 10 over 9, which means my area is both of those squared. That'd be 100 over 81. That was one of our questions. For our other one, we were supposed to find DE. Well, DE would match up with part of this one. Well, what I did is I said, well, AC over AE have to be the same length, or have to be the same ratio. So AC over AE, so I wrote that there. Well, length AC is 11 plus 9, which equals 20. AE is 10 plus x. So I have 10 plus x. Well, that equals our scale factor of 10 over 9. Then I just need to solve for x, because x is actually this length here. Do all the steps on the surface make sense? Okay, good. Other questions? Yeah, Hamza.
So on this one, if you were to like draw each triangle, ABC and then EBE, would the same letters, like would A and A always match up on the drawing?
A and A will always match up, yes, because they're the same angle.
Okay, because sometimes like they're the same letter, but they don't match up on the drawing. That's some kind of problem with that.
Yes.
Yeah, so like when would that happen?
That would happen if, perchance, I'm not going to try to emulate it 100%, but let's say I have, this can be a terrible example, but let's say I call this A, right? And I'm talking about these 2 triangles. This angle right here would most likely match up to maybe a different angle, maybe this angle down here. It's when they aren't the exact same angle. So if we notice A is the exact same angle here. And here, A is this angle. And in the other triangle, A is this angle here. So it's 2 different angles. But it still shares the same letter. This one, A is just A. It's not separated. It's the same angle in both of them. And this one, A is a different angle in both of them.
So that'll happen when the angle is separated?
When the angle is separated, yes. Yeah, yeah.
For it to be similar drawings, it doesn't have to be the same size, right?
Correct. Similar triangles do not need to be the same side. They just have to preserve a ratio. Other questions? Okay. Then let's go on to today's lesson. Yesterday we said we can have an area ratio if two objects are similar shaped. We find the scale factor, we square it, and then we have our area ratio. Today we're going to talk about triangles in specific, triangles that are not similar. These two triangles are not similar that are on here. In fact, our first one, does ABD even look similar to DBC? No, they're not similar. But they share a very key characteristic. They have the exact same height. So if we look right here, they have the exact same height. They go to the same point. Remember, height is a 90-degree angle that we can carry to both of these triangles. So they have the exact same height. So if I was going to compare the two areas in a ratio, I would say, well, the area of triangle, let's call it ABD, and we'll do that over the area of triangle, let's call it, BCD. They're not similar, so it doesn't matter how I label them. Well, triangle ABD, the area is going to be half your base times your height. Well, remember, your height and your base create a 90-degree angle, so the base is going to be A for this one. And our height is just that H. Now for the other triangle, my base is B, so we're going to have 1/2 B times our height. Well, whenever you have the same thing on the top of a fraction as the bottom of the fraction, they cancel out. They turn to just 1. So 1/2 will cancel out with 1/2. It just turns to 1. And H over H just turns to 1. And you're just left with A over B. In other words, if they have the exact same height, it's just going to be base 1 divided by the other base. We'll call it base 2. And that is your area ratio. Did I square it? No. The only time you're worried about squaring or taking the square root is if you have similar triangles. These aren't similar triangles, so that A over B is in fact your area ratio. This is your area ratio without squaring. So, if two triangles have equal heights, then the ratio of their areas are equal to the ratio of the bases. Ratio of bases. And that would be basically base 1 over base 2. I'm going to re-emphasize that. That is, in fact, your area ratio. Students really struggle with the fact that I don't have to square it. You don't have to square this one. That is only when you're dealing with similar objects. And this only works for triangles. This is only for triangles. That's all we're covering today are triangles. Our next case is what happens if they have the same exact base, but they have separate heights? Who wants to just take a guess at what the area ratios are going to be for that one? Hamza.
Both of their heights, like H1 over H2.
That's exactly what we're going to end up doing. We're going to go ahead and prove that, but that is 100% true. Same bases is one of the easier ones to pick out. You actually have to have triangles that are linked up to the exact same length here. That's how you're going to know they have the same base. All right, so that one definitely has the same base. And if I was to do area of triangle, what do we have? ABC over the area of our other triangle, that would be ADC. We would have half a base times height. Well, our base on this, on ABC, is that big B. And times our height. In this case, our height is this H letter here. It's 90 degrees to the base, so it is our height. So it's half of base times height. Our other one has the exact same base, so it's going to be half of B times, but this height is actually length K. Once again, our 1/2 will just turn to 1. B divided by B is just 1. And so we're just left with h over k, which is that height 1 over height 2. All right, so if two triangles have equal bases, their area ratio is going to equal height 1 over height 2. In other words, the ratio of heights. Which would be the same thing as height 1 over height 2. Once again, that is my area ratio. Did I square anything? No, you have to keep that straight. The only time you're squaring it is if you have similar shapes, like similar triangles. If I'm just doing same base or same height, you're not going to square anything. But that is still your area of, or your area ratios. Yes, ma'am.
For the ratio of heights, could you also just say h over k?
You could absolutely say h over k. However you want to put in your notes. These are your notes, whatever makes sense to you. All right, that means for 1, 2, and 3, we're just asking ourselves, do they have the same base or the same height? So in number 1, is that the same base, or do two triangles have the same heights? Yeah, they have the same base. So same base. If it's the same base, we're looking for h1 over h2. We're just trying to compare our heights. So it says in the direction we're supposed to do triangle ABC over ADC. So let's do it that way. Let's go ABC over our ADC. Well, the height of ABC is 9. So we're going to have 9. And the height of ADC is 5. So we're going to have 9 over 5. And just a quick reminder, that is our area ratio. All right, number 2, does that have the same base or the same height or neither? Same height, same base, or neither for number 2. Sam? Same height. They do have the exact same height. In fact, if we look here, we have a 90-degree angle. That 12 line goes to the top of both triangles, so our height is in fact 12. What you'll see sometimes is you might see it written off to the side where your height is that one. So they do have the same height, which is actually 12. Maybe you'd have that. So same height. So we're looking for base 1 over base 2. Once again, we're going to go ABC over our ADC. So they have the same height, so we're looking for our bases. Our height creates that 90-degree angle, so the base of ABC is going to be 9. The base of ACD is going to be that 16. So we're going to have 9 over 16. All right, final one. Same height or same base? Same height or same base for the next one, or neither? Grant?
Same height.
They have the exact same height. I know we have one height is 8 here because we have that 90 degrees, but we can see that slides right over and matches up with our ABC. So in your head, you should kind of visually be able to see this happening. That is also 8. So it's going to be the same height once again. Our height and base create a 90-degree angle. So if you look at ABC, that 90-degree angle is created with that 8 and that 10. So we're going to have 10 over. And the other one, we have that 8 and 12 forming 90 degrees. 8 is our height, so 12 must be our base, which we can rewrite as 5 over 6. Hamza.
So we only do this when we don't have similar triangles?
Yes, that's a good way to think of it, because your first question is going to be, are they similar? Mm-hmm. If not, look for same base and same height. Because we do have 3 ways to prove or to come up with our area ratio. The first two are what we covered today. These first two only work for triangles. 1 and 2 only work for triangles. 1 says if two triangles have equal heights, then compare their bases. Number 2 says if they have equal bases, then compare their heights. These are your area ratios for triangles that have same bases or same heights. Number 3 is what we did yesterday. It says if you have two similar triangles, this in fact works for any similar shape. So you could have two similar pentagons, two similar rectangles. So number 3 works for all of them. 1 and 2 only work for triangles. Number 3 says if two triangles are similar, then you find the ratio of their areas is going to equal the square of their scale factor. So if you have similar shapes, you're always going to find your scale factor and then square it. So number 3 is the only time you're worried about squaring numbers. 1 and 2, you're done. Base over base or height over height. You have your area ratio. Number 3 is the only time you're worried about squaring numbers because you do have to square your scale factor. Keep all 3 of these straight. Don't get them confused on the test because the worst thing you're going to have is you're going to get back that you squared every single one of these that you were just comparing heights because you thought that meant area. Squaring your scale factor only happens on number 3. All right, let's continue. Are regions 1 and 2 similar? Before I ask your input, I want you to be clear of what I'm asking. Area 1 is that triangle. Area 2, I'm just looking for the one that has 2 on it. Are those two shapes similar? Yes. No, they aren't. They're not even the same shape. This is a trapezoid. One is a triangle. So no, they aren't similar. Nope. Can someone name 2 similar triangles, though? Can someone name 2 triangles that are similar up there? Arian.
ABC and ADE.
Yeah. ABC is similar to triangle ADE. And we could go ahead and prove that because both of those triangles share angle A. And because of the parallel lines, the bottom left hand of each triangle are also congruent. 2 congruent angles means 2 triangles are in fact similar. So we have ADE is similar to ABC. I do want to note that if I draw just regular ABC off to the side, we have a length 5 on there. And that is similar to that small triangle. Let's go ahead and use that tool. So that's going to be similar to the one that has a 2 on it, which was our ADE. Let me move that similar sign up a little higher. You didn't necessarily have to rewrite these. It just can help with the numbers. What's the scale factor between those 2 triangles? What's the scale factor between, let's go small to large. What's the scale factor of small to large? So I'm starting with the scale factor. Small triangle to large triangle. So that's area 1 compared to triangle ABC. What is just the scale factor, Ishana? It is 2 to 5. What's the question asked for, though? It asks for the ratio of areas. The ratio of areas. What's the ratio of areas between the 2? Ishana, you want to finish this one off?
4 over 20.
It's going to be 4 over 25. They are similar triangles, so our ratio of areas needs to be squared. So that would be 2 squared over 5 squared, which equals 4 over 25. Note that this is the area of ratios between area 1 and triangle ABC. That's our area ratio of 1 to ABC. Our next question is, what is the area ratio of 1 to 2? Area 1 to area 2. That's where it gets a little more complicated. You have to think what area 2 actually is depending on what we know. I know area 1 compared to triangle ABC. But area 2 is equal to triangle ABC minus area 1. Let's make that a little more prominent. Do you all agree with that statement? Area 2 is ABC minus the top. All I'm saying is, if we have that entire triangle and I took a big eraser and did this, we'd be left with area 2. That's all I'm saying there. Well, we know how ABC compares to area 1, which means I can actually get this area 2. Let's go ahead and do that. So we're doing area 1 and 2. It's going to be the exact same thing as 4, that's my area 1, and it's going to be over 25. But note 4 is in place of my area 1 in the ratio. So instead of just being 25, we're going to subtract 4 away from it. That is our triangle ABC from right here is 25. Our area 1 is that 4. So it's ABC minus 4, which is going to equal 4 over 21. So in the ratio, our area 1 is 4. In the ratio, ABC is 25. So 25 minus 4 is going to leave me with the area 2 in that ratio. Yes? Yeah. Are there any questions on that? Yeah, Hamza.
So it's area 1 over area 2 equals 4 over 9 minus 4.
Area 1 over area. Yes, that's what we have right there. We have that 4 is our area 1 over that 21 in that ratio would be our area 2. Because area 2 is ABC minus 1. That's what we said right here. So in a lot of these problems, you're just going to come up with parts of it, and you have to figure out big picture-wise what's happening. 2 is ABC minus area 1. I figured out what ABC and 1 have to do with each other in a ratio, and I use that to come up with my area 2. Okay? All right, let's continue, and let's do these last two problems. We're supposed to find the ratio of the areas of 1 and 2, and then 1 and 3 in both of these. So first of all, we're going to compare area 1 and 2. Do they have the same height or the same base? Or are they similar? First of all, are they similar? Are 1 and 2 similar? Probably not. So do they have the same height or the same base? Do areas 1 and 2 have the same height, same base, or neither? Tori?
Do they have the same height?
They do have the same height. Yep. Because if I would draw a little red line coming down here, that actually works for all three triangles, doesn't it? Yeah. So all three of them are actually the same height. So 1 and 2 are same height. So we're going to compare the bases. Well, the base of 1 is 8. The base of 2 is 5, so it's just 8 over 5. For B, we're comparing 1 and 3. Well, thanks to Tori, we already know that those two are the same height. It's the same line. So same height. The base of 1 is 8. The base of 3 is 15, so we have 8 over 15. All right, our next example, we are comparing 1 and 2. This is the slightly harder of the ones. They don't look like they're going to be similar. I can't prove that two things. So I'm either looking for same height or same base. Who wants to take a guess at this one? It's either same height or same base. You have a 50-50 shot. Doesn't always come that nice in this class. Hamza?
Same base.
They will not have the same base. And that's kind of what I was looking for as an answer. Note, to have the same base, they actually need to share a base. So if I look at, see this base here?
Oh, yeah.
Does 1 actually have that base?
No.
No, because that would be up here. And if I look at the other one, this 2 is 4, does 1 share that exact same base? No. So then I'm going to look, so kind of same base generally stands out a little bit. Most of the time it kind of looks like this, where you can actually see them overlapping the same base. So it is in fact going to be same height. And the problem with this one is it's turned weird. If you just turn your paper so that 7 and 4 become your bases, you're going to see you can actually draw a height to both of them. That would look something like that. Do you see this height here?
Yeah.
It's the same height to both of them, right? It's a right angle to both their bases, and it goes up to their top. So they will have the same height. So these would have the same height. Does that make sense?
Yeah.
You sure?
1 and 2 have the same height, or
Yes.
1, 2, and
3 does not have the same height.
Okay.
That's going to be slightly different. We're just doing 1 and 2. Same height, so we're going to compare the bases. The base of 1 is 7. The base of 2 is 4. B is going to, Hamza, is kind of what you said. If they're not similar, then we look for same height and same base. 1 and 3 are actually similar triangles. They are similar triangles because they have vertical angles, and because of the parallel lines, alternate interior angles would make kind of those two congruent. So 1 and 3 are similar. If they are similar, you first have to have a scale factor, and then you have to turn that into your area ratios. So we're going to start with a scale factor. And short of redrawing them, just look at 4 and 7. They both go to their corresponding parts. 7 goes from the one with the 1 tick to the 2 ticks. 4 goes from the 1 tick to the 2 ticks. So those are definitely corresponding parts. So our scale factor of 1 to 3 is going to be 7 over 4. Is that my area ratio, though? Grant, what do I have to do to get my area ratio?
Square both.
Square both. Similar triangles mean I'm squaring my scale factor. So our area ratio is going to be 49 over 16. Okay, I know we don't have a ton of time left, but I want to start one of the problems with you because these are kind of the hard ones. We're going to start 24 together.
What was the area ratio?
49 over 16. These are going to be the harder of the problems. They're all on there, but I want you to make sense. I try to put this as best I can, but it can be a little confusing. So first of all, let's look at the shape. We're supposed to compare 1 and 3. 1 and 3. And kind of what I'm going to help you out on here, it does say that we do have trapezoids. But long story short, 1 and 3 are going to be similar. That is the first thing. A says compare 1 and 3. Well, 1 is going to be similar to 3. So that means we're going to have a scale factor. What's the scale factor from 1 to 3 in this case? Yeah.
1/2.
1/2. It'd be 5 over 10, which would equal 1/2. That means our area ratio for this one would be 1 over 4. That is your answer for A. B is the more complicated one that I wanted to get to. B says compare 1 and 2. Are 1 and 2 similar? Or can you look for a way that would prove they're similar? No. So then you're going to ask yourself, do they share a base at all? So 2 has this base. So let's look at their bases. 2 has this base. Does 1 also have that base? No. All right, 2 has this base. Does 1 also have that base? No. So they don't have same bases. Bases have to be on the outside. They can't share. So this wouldn't be a same base situation. So that must mean they have the same height. And they absolutely have the same height. So if I look at this 90-degree angle, they have the same height. Well, if you have the same height, you have to compare bases. Is my base 1 or base 2 labeled? No, it's not. But we actually have the answer right here. We have that answer from part 1. So let me erase 2 for just a second. I'm going to erase this triangle for just a second. We compared 1 to 3. What was the scale factor we came up with 1 to 3? What's the scale factor we came up with for 1 to 3, Leanne? We came up with 1/2. That means every single side from 1 to 3 will have that same ratio. So this length to this length will preserve that same ratio. In other words, if this was 1x, this length would be 2x. That's what that ratio means. So this length here to this here is 1 to 2. Well, when I bring this triangle back in, this is still 1 to 2. The ratio between this length and this length is still 1 to 2. These are our two bases. So your ratio between these two is going to be 1/2 because it has the same ratio. I'm just looking for the ratio of the bases. And I said the ratio of the side from 1 to 3 is 1/2. So that means the same sides, they don't change because I brought another triangle in, is still 1/2. I did try my best on the answer key to write that out, but maybe it'll make more sense now that I went over it in class. All right, guys. What do we have? We have like a minute left. Let's say just have a good day.